You did.
Yeah.
Yeah.
You took the, well, because you prepared everything so well, you put it in a calendar with the right link.
I think it's also because you are listed as a co-organizer, so you can always log in as a panelist at any time on any seminar.
Excellent.
You have
Okay, can we do things like check that we can share screens? I'll go first.
Sure.
Yep.
And tell me if this works.
Yes, it does.
Yep. Okay, and
That's so serious on this photograph.
Peter, if you can do the same.
Yes, I will try to do that. Let's turn this one off.
Does it matter that I have a non-standard background?
Do you want one?
No, I'm quite happy after I took the time to make this one.
Yeah, keep this one then. It's okay.
Yeah, okay, so I don't see these. Where's the, there's the share screen thing. So if I do share and I start this one, it's come up correctly.
Yes, it works.
Slides, okay, cool.
Good.
Yeah.
I've got too many slides, I guess, but anyway.
Do you want to play the videos just to make sure they work?
Like this one, suck.
Yeah, all good.
I want to have the text appearing later, but anyway. Tuck. Oh, this comes with sound. Can you hear the sound? The sound. No.
Yeah, it's best without the sound. I'm not too fan of the sound effects on that one.
Why does it play a sound suddenly? I didn't have that before, so.
Oh, yeah, look.
Oh my God. How can you somehow stop the sound of the videos, or is it just not possible?
I think oof, that's gonna be a tricky one.
Yeah, anyway. So I have to warn people before that.
Usually I can see the sound control inside my
yeah,
player.
in the player. Here we don't
See a sound control there?
on the right hand side. Yeah.
Okay.
And once you've switched it off once, usually it stays off. Or maybe you've got to go back into creation mode.
There. No. If I click something there, then goes to the.
Maybe you need to
Stop
come
sharing.
out of the showing mode.
Yes, if I go there and then
Yeah.
in the video movie tick to controls.
Yeah, volume is there.
Sound
Just in
volume.
the volume in the control bar.
Oh, this one, yes. Let's try this again. You're cleverer than me. There we are. Perfect.
So awesome. Much better.
Agreed.
Excellent. You're perfect. So yeah.
Okay.
Good.
Do you agree that I present Remade just to keep people busy while they're arriving? So the first
yes, of course. Yeah.
3-4 minutes is an intro to Remade. I will mention you at the start, but I also mention you again just before. So I will get to the slide that is the series of presentations.
Yeah.
And that's where I introduce you.
And I will launch the YouTube streaming after the introduction, if that's fine with you.
Yeah, sure. You mean recording?
Yeah.
Yep.
Okay.
Indeed.
So my introduction won't be recorded.
Unless you want to.
Oh no, I'm really happy about that. I'm improvising.
That's what I got from your email.
I'm improvising with Marie's slides, and it's always different to if you wrote them yourself and thought about what you wanted to say. So
I'm showing very secretive results. They won't be publishable. Please don't record. No. I'm not playing the Ralph Gillis.
No, it'll be fine.
No, I went through the talk by Sarah Rogers, And that was excellent. My God.
Yeah.
I won't reach that level, but no, it was great. I know, fantastic. Really like that.
Which
Remember
one
to,
was this one? I'm not sure
Being
I
a
know.
native speakers often they I don't know, somehow they're really well trained in this, and then of course it's their natural language as well.
It helps.
Peter, go slowly. Remember to give people time to think.
Mm.
Okay, so don't go too fast between transitions,
Yeah.
because we're still thinking about what was on the last slide before you start on the next one.
I'm trying to keep that in mind. That's a very good reminder anyway.
Yeah.
Right. I know nothing about you. All I can say is you're in charge of 2 instruments at the ILL.
One instrument was.
Okay. You need to update your webpage on the ILL website.
Oh my God.
Busted.
And I can also tell them that you haven't had a publication since 2010, or maybe that's something to do with updating your website.
Double busted.
I completely forgot that this exists still. It was, yeah.
All right, I won't say anything like that.
Thank you.
Thank you, Gary. That's really kind of you. We keep that private.
Please visit my website.
Okay, I'm going to switch off my camera and microphone, but I'm around here. If you need me, just use the chat box.
Okay, and we are to accept questions, I presume. Hopefully I'll be able to see them, because that's often a challenge if you're host.
Yeah.
Well, I can ping you if there's one coming.
Oh, that's a good idea, yeah.
And I'm going to start the webinar now. So if we have early comers, they can start joining the audience.
Okay.
Closing my door. Might help as well.
Peter, you have 4 or 5 minutes before you're on. You're welcome to switch off your video and relax until I get to the slide with the list of speakers from the last year.
Perfect. I'll let you do the job.
All right. Hello, good afternoon. I'm Gary Evans from the SRF, the European Synchrotron, here to introduce the 10th webinar for Remade Atari from Peter Fouquet of the Institut Langevin, France, the European Neutron Source. While we wait for other people to join, I'm going to give you a brief introduction to Remade Atari. We're a European project with 15 million euros to give a boost to the circular economy, particularly for recycling circular materials. We're here to help scientists in academia and industry by helping them to use analytical tools to explore the properties of materials. We are 44 or more analytical research infrastructures offering access to more than 50 instruments. With synchrotrons, neutrons, free electron lasers, high magnetic field laboratories, ions, positron beam facilities. We're all over Europe, and access to Remade gives you access to all of these facilities. There are 3 paths to access. Remade TNA is for academia and industry. You can submit a pre-proposal at any time. With a pre-proposal, this is really just a paragraph describing what you want to do and any questions for our experts, and we will guide you. The pre-proposal doesn't commit you to anything. It only asks us for help with your problem. When you've got our feedback, you can submit a full proposal. There are 2 calls a year, and the next deadline is the 10th of April. Remade SME is for small, medium companies. It's completely confidential. You can use mail-in, and we'll even help you with data analysis. Remade IND is a partnership between a knowledge provider, who can be an academic or a research and technology organization, and an industrial. And here, the knowledge provider will take in hand the industry problem and carry out materials characterization at the various infrastructures across Europe. We also will compensate the knowledge provider for the time they spend and their expenses in their research. So industry benefits from both Remade Atari's help, that is the research infrastructures, and also help from a knowledge provider. This is the 10th webinar in the first series of Remade webinars. We will begin a new series shortly. So here today, it's Peter Fouquet from the ILL in France. That is a European neutron source. And he's going to tell us about neutron spectroscopy studies of hydrogen and oxygen diffusion in energy materials. Peter, are you there?
Yes, I'm there. Thank you.
I'll stop sharing. And it's over to you. Please tell us about neutron studies.
Yeah, thank you, Gary. Thank you, everyone, for giving me this platform to talk to you. I hope you can have a nice start of the Friday afternoon, just leading to the weekend. And I will start screen sharing if I manage to do this quickly. Good. Suck. I hope you can see this well now. Let's start the presentation. So today, our aim is to have a look at what neutron scattering can do, and specifically neutron spectroscopy, because we had already 2 talks by neutron experts, and they were covering what you can do with, in particular, small angle scattering with Sarah Rogers, and Ralf Gillis talked about battery applications. So I wanted to focus today on an overview what you can do with neutron spectroscopy. And I will have some quite specific examples that also show how you can link the neutron spectroscopy with the knowledge you gain from other techniques. So just to give a short content overview, I will first talk about a little bit why we want to use neutrons, how they are produced specifically at ILL, a reactor source. Then a little bit about different spectroscopy techniques, and without going into too much detail. And then I will try to cover in my time a few scientific examples to give you an overview of what you can do and how it's done. So the neutron sources that we have in REMATE, there are 5 of them. They are all members of the network LENS. We have in the UK ISIS as a spallation source. We have PSI in Switzerland, who have a synchrotron and a neutron source, most notably. We have the Hans-Meyer-Leibniz-Zentrum with a reactor in Garching next to Munich. And in Budapest, we have the Hungarian neutron source BNC. And last but not least, ILL, the Institut Laue-Langevin, based on the same campus as Gary's institute, the ESRF. So we have also, like at PSI and like on the ISIS campus, a synchrotron and a neutron source on the same site. Why do you use neutrons? Already Sarah touched that a little bit. Just as a reminder here, the neutrons are electrically neutral, so they can penetrate deep into matter. They have a spin, a nuclear spin, so with that you can also look at magnetic diffraction, for example. In the energy range with which we use neutrons, you can get an angstrom range wavelength, which means that in terms of scattering properties, in terms of diffraction, you can get a spatial resolution of the angstrom range as well, which is important to look at matter on an atomic length scale. And finally, you have very low kinetic energy. So for us, it's pretty easy to get milli-electron volt energy resolution, or even down to micro or nano electron volt in some extreme applications. And what's very interesting, that makes the neutrons very complementary to X-rays. That's shown here on the right-hand side graph. When you look at this, at the scattering cross sections of X-rays on the left and neutrons on the right, you see that X-rays, the scattering cross section is guided by the number of electrons in the material, in the atoms. Whereas for neutrons, we have a nuclear interaction, and by quantum mechanical effects, the neutrons have the highest scattering cross-section for hydrogen, which makes this hydrogen very, very visible for us. And you can play also using quantum mechanics, some other tricks. You have actually a negative so-called scattering length for hydrogen. And this means that if you have the right mixture of hydrogen and deuterium, which is the variant of hydrogen with 1 neutron more, then you can get reduce contrast, or you can pronounce certain parts of a sample, of a hydrogen sample, and change contrast in your sample and make some parts of, for example, polymer assemblies visible and others disappear. It's used in this research, for example, with small angle scattering that Sarah showed. Now, we produce the neutrons with a reactor at ILL. And what you can see here is a cut through the reactor building. And in the middle, we have the center of the reactor. That's where we create our neutrons with a nuclear reaction. And they are extracted around the core of the reactor with neutron guides and brought to the instruments. Now I have a little animation of first how the neutrons are created. So whenever you have a fission process, we create 2.5 fast neutrons. And these neutrons, they can partly be extracted, and part of them are used to maintain the nuclear reaction. And with this process, we can get at ILL a very, very high flux of neutrons that we can use as light source. But you have to think of our neutrons as kind of this very specific kind of light, just like the X-rays you have in a synchrotron source. Now, when you look at this assembly here, we have several fingers showing next to the reactor. And what we do there is we have several containers of cold liquids next to the reactor, just to tune the distribution of energies of the neutrons. The colder the source that we have, it's just like a light source. The colder the source, the colder the light. I show you in a little film here how this is done. So the neutrons come out of the reactor. They go into the guides after they have been in the energy moderator. Then they come to energy selecting monochromator, then the sample, then an analyzer, and then they are detected, artistically shown here. And with that, you can get information about how these samples move in our case. You can either look at the positions or how they move. And what we are with spectroscopy concerned with is the motion of the atoms in the samples. Now, the whole setup at ILL is shown here. We have on the bottom left corner the reactor building. There are quite a few instruments already in the building of the reactor. And then there are neutron guides, which are mirror assemblies, basically, which guide the neutrons out to instruments that can be up to about 100 meters away from the reactor core. And they are all in 2 large guide holes. And that's where you would find the instruments when you do experiments at ILL. Now, the spectroscopic window that we can cover, that's shown here. I extracted that from a relatively recent publication. And you see here in this graph, maybe you can look at that later more in detail when we have the YouTube video of this seminar online. Just to draw your attention to the center, we have different types of spectroscopy, all these colored blobs here that are different neutron spectroscopy techniques, time of flight spectroscopy, backscattering spectroscopy, spin-echo spectroscopy, and they can cover huge ranges. Oh, I wanted to go back here. Huge ranges of length scales. So you see these length scale displayed on the bottom line here. So that goes from the micrometer to the nanometer, from the micrometer upwards, from nanometer upwards. And then you have the time scales that are between microsecond and picosecond and below. And this can all be covered at the same time. And the nice thing about neutron scattering is that you get the spatial information and the spectroscopic information, the time information in the same time. And just for comparison, you see quite a few different Other spectroscopic techniques in comparison to what we do, you have infrared spectroscopy, Raman spectroscopy, dynamic light scattering, X-ray spectroscopy techniques. So it's a wide range of different types of motion that you can cover with this. And here we will just cover a few examples. Now, in a generalized way, what you do in a Neutron scattering experiment or any spectroscopy experiments, you come in with a pretty white light. You apply energy filter, do scattering from the sample. Then you apply further energy filter and you measure the signal in the detector. And the information that you extract, normally categorize it by splitting it up into what's happening in different momentum transfers and different energy transfers. And you do that because splitting this up in this way gives you a lot of information that lets you compare the data to, for example, molecular dynamic simulations. Now, the first spectroscopy that I want to just highlight that we have, for example, at ILL, that's the vibrational spectroscopy. That's on the fast neutron end. And one very useful spectrometer that we have for looking at hydrogen-containing materials, for example, is Lagrange. Lagrange is a very recent and very, very high flux instrument where you can use, in Neutron standards, very small samples. You come in with a beam from a monochromator that comes directly from our hot source, illuminate the sample, and then you have a large shield of, well, you can see it better in the 3D view around here, that large shield of monochromator crystals. So they select an energy, but they are built all around here. And then you illuminate with this detector at the bottom of the instrument. And this gives you a very large signal. And then scanning through energies, you can record a spectrum. And here's an example of hydrogen in a C60 buckyballs. And you see the very lines that you can detect. And this spectroscopy, of course, covers a similar spectral range as, for example, Raman and infrared spectroscopy. But you can investigate with this samples which are not available for, not attackable with Raman or infrared, for example, because they are black and not transparent to light. Now, the second spectroscopy technique that we use very much here at the Neutron facilities, that's the time-of-flight spectroscopy. That's the spectroscopy. Here I show you a spectrometer IN5. In that spectroscopy, you have a white beam of cold neutrons that come from a liquid hydrogen source from the close to the reactor, and then this beam is chopped into little pulses with so-called chopper disks, which are blades with holes in them, and they cut this neutron beam into pulses that fly through the instrument, hit the sample, and then you have a detection of the signal at the detectors all around. And you can see it here in a 3D print. And as a function of time, you see when the neutrons arrive at the detector. And arrival time that can be recalculated into energy transfer, because time is related to a speed of the neutrons, and speed is related to the kinetic energy. And that lets us deduce afterwards if we have, for example, excitations, or if we have other diffusive energy transfers at the sample. Now, a last technique that's very specific for neutrons. And that's the spectrometer where I work at, the spectrometer WASP at ILL. There we do a very high resolution technique by exploiting the neutron spin. And we expose this spin to a magnetic field. And with this magnetic field, we split up the wave function of the neutron in two parts. These two parts will interact with the sample with a time difference t, and then recombined in the second half of the spectrometer with an opposite magnetic field. And then at the end of this spectrometer, you can measure the loss of polarization of the spin property. And this loss of coherence, that shows you if the what the structural correlation function does at the sample with time. So this Neutron spin echo spectroscopy measures the decay of the structural correlation function with time. So that's the high resolution, one of the high resolution techniques. And now I want to go to scientific examples. And I start with a very specific example where I'm involved in myself as a thesis supervisor. And that's a project that we do with a university in Germany, with Westfälische Hochschule. And there we look at the mobility of hydrogen and the reactivity of hydrogen in some catalysts that are alternative to platinum. Why do we do this? We do this because well, hydrogen is a very important energy carrier if you want to look into a more circular economy in the future, where we want to get away from fossil fuels and to reach larger ranges, and especially in heavyweight transporters on road, lorries, or on sea. Hydrogen is a very good energy carrier that scales very well if you upscale the load when it gets very complicated for batteries to operate. But for the production of green hydrogen, we have a big bottleneck at some point, because there's a catalyst that you need for this when you want to break up water into hydrogen and oxygen. And at the moment, this is largely done with platinum and iridium as catalysts. And they are, first of all, extremely expensive compared to other materials. And they have to be extracted from the ground, and they are effectively very rare. So if you upscale the production to what would be needed in the future, it's hardly invisible to cover this all with platinum and iridium. So we need to have alternative catalysts. And that's what we are working on. So this molybdenum sulfide that we are working on is a layered material, and it's highly porous. And of course, there have been studies on the structure, but about the mobility of the hydrogen in this material, it's very little is known. And what I find interesting in this case as an example is that here we already, before Remade started, we saw the need to cover quite a few different techniques that are a part of Remade, most notably, of course, neutron powder diffraction and spectroscopy, but also different X-ray techniques, diffraction, spectroscopy, XPS, and NEXAS, but also beams, nuclear reaction analysis, and infrared and Raman spectroscopy. Now, for looking at this, we had to if you look at these samples and want to study hydrogen motion, you're often confronted with the fact that there's also water inside, of course, because you have basically the whole process happens in water. So you have to look at differentiating the motion of the different hydrogens in your sample. So what we did is, first of all, we looked at very specific samples. We looked at molybdenum sulfide single crystals. You can see them here just as a general image, and here you see them put in a sample holder. It's a flat aluminum cell of about, the inner part is about 2 by 3 centimeters. And we looked at different kinds of sample preparations. Once we soaked them just in water without any chemistry attached. We atom bombarded the single crystals, and we loaded them via electrolysis. Now, then we exposed them to the different techniques that are at our hands. So for the soaked crystals, so just soaked in demineralized water, when we looked at them with the nuclear reaction analysis, where you expose the samples to an ion beam, you can look at the depth profile of the hydrogen. And there you see basically no hydrogen in the sample beyond the absolute surface layer. There's no signal in the deeper depths. And also when you look at XPS, there's, and then heat up the sample, look at the sulfur line, at the molybdenum lines, oxygen line here for comparison, and there's not much happening basically. So no chemistry happening. The water is only physisorbed on the surface. And when we look at the neutron scattering, what we did there is we went to a time of flight spectrometer, and we looked at the broadening of this elastic line. That's what's called quasi-elastic neutron scattering, and that tells you something about the diffusion. Meaning that when the particles, in our case the hydrogen atoms or the water, move in the sample, then the elastic line will be broadened, and you will see a slight foot here that's typically following a Lorentzian broadening. And we saw such a broadening, so we saw some motion. And the analysis showed that this pretty much can be modeled by the diffusion of liquid water. So it's just the physics of water in cracks that we see. In the hydrogen beam bombarded molybdenum sulfide, we saw a very nice penetration into this sample in nuclear reaction analysis. So here we see in deeper depth a substantial signal, and we saw some signal on the first day, but then even much stronger signal a few days later after aging. So there is quite substantial uptake of hydrogen on these samples and some slow diffusion process into this layered crystal after days. We also saw when we looked at XPS, heating up the sample, that there is reactivity. There's not much happening on the molybdenum line, but the hydrogen seems to be strongly bound to the sulfur, and there's chemistry happening there. Now with the quasi-elastic signal, we see a bigger broadening than what we saw for the water-soaked samples. And here we see, interpret what we see as a diffusion of hydrogen ions. And we can also follow how with temperature, how this hydrogen desorbs. Basically a total desorption of the mobile hydrogen by 500 Kelvin. Now for the electrochemically loaded samples, where we really did model the process that you have when you do the electrolysis. There we saw even much bigger uptake of hydrogen into the sample. We saw much stronger changes in the XPS, in the X-ray spectroscopy, not only on the sulfur line this time, but also on the molybdenum line. So it's very strongly anchored. There's a lot of real reactivity happening there. And what we also saw is when we looked at the data with quasi-elastic neutron scattering, and these measurements were done in Munich at MLZ, there we saw actually two different lines in the quasi-elastic signal, means that we saw at the same time different processes of diffusion. And as one of the processes quite close to the speed with which we saw the diffusion in the atomic beam bombarded sample, we believe that we see really H2 motion, and we see hydrogen atom or hydrogen ion motion as well at the same time. So the conclusion of this, and it's nice to have all these different samples and have all the different techniques. And I think that's also the richness of the overall remade projects, that you bring these different analytical techniques together, because that provides the essential tool for understanding very complex systems like these systems. And what we found is that the liquid water actually, as you would expect normally, does not do real chemistry there, but you can access defective regions of the samples, so you have quite strong water uptake, but it doesn't go subsurface. In atom beam loaded samples, the proportion of mobile atoms increases with temperature, but you can also get complete desorption afterwards. That's not the case for the electrolysis loaded samples. They still keep quite a bit of hydrogen inside, trapped, and you see different diffusion processes there. Now I want to, after closing this, just show very briefly two other examples. One would be hydrogen diffusion in carbon materials, and that's a typical example of hydrogen storage materials that can be produced quite ecologically from existing carbons. And there we looked with a group from South America on a newly produced nitrogen-doped porous carbon. And in this study, we looked in particular on hydrogen motion as a function of temperature compared to normal exfoliated graphite carbon. And you see that the mobility is very, very strongly rich for this one, making very interesting storage material. You also have a very high hydrogen content for them. They can take up a lot of hydrogen. And you see this here compared in this plot of diffusion constant versus inverse temperature. Now, a different study that's very recent from colleagues from UCL in London, Fabrizia Foglia, and also CA has been at Grenoble has been involved in this. This is a study of the motion of hydrogen in all its forms, in the form of ions, in the form of water, in the form of being part of the polymer in fuel cells. And they looked at how these different parts of the hydrogen move in this example, anion exchange membrane fuel cells. And the interesting part of this is that you can really look at the polymers themselves or at the try to look at specifically build fuel cells for the neutron experiments. And by combining the different spectrometers, you can get a huge range of dynamics, easily 9 orders of magnitude apart. And by separating them out, by changing the temperature and by changing the relative humidity, you can really distinguish the different motions and get a lot of experimental information that's otherwise only available via calculations, molecular dynamics or DFT. A final science example would be also in the energy field, example of spin echo measurements that we did on non-fullerene organic solar cells. So there you can go through different points in the constituents diagrams of the different of the polymer blends, mixing different polymers, and look at the dynamics really as a function of momentum transfer, as a function of temperature, and trace how these mixtures changed your overall dynamics very much in detail. And also that's a very rich point where you can, with techniques like the Newton spin echo, you can look at the function of the dynamics as a function of time. Whereas with time-of-flight spectroscopy, you can look at the dynamics as a function of energy exchange, which are properties that are related to each other via Fourier transform. So you can get very global picture with these, combining these. Now I want to thank and list a lot of collaborators. I certainly have forgotten 1 or 2. I apologize for that. And for the funding that we receive for all this research, and I thank you for your time, and I'm open for questions. Thank you.
Thank you, Peter. Does the audience have any questions? Please put your questions in the question and answers. For the moment, we have no questions, so I will proceed to continue with presentation. Can you stop share? Thank you. Thank you, Peter. That was great. I'm now going to announce the next. Sorry, first of all, we will put into the chat a link to a survey. Can you please, the audience, can you please go to the survey, tell us what you think, and maybe give us suggestions for future webinars. And announcement of the next webinars are on the 26th of April, we have Kim Nygaard from Max 4, multiscale structural characterization by scanning SWAX imaging. And on the 26th of June, Anna Makova, NPI, in the Czech Republic, ion beam modification and synthesization of materials and surfaces for sensorics by application of photocatalysis. You can look at the full list of webinars on remadeproject.eu. We will have others to announce. At the moment, we're organizing the dates with the authors. So please go to the chat to collect the link for the survey. And last chance, are there any questions for Peter? I don't see anything, so thank you all for watching, and until next time, goodbye.